GIPSY is a program which stands for Graph Isomorphism Problem Solved Yes. GIPSY, as the name connotes, solves the graph isomorphism problem by using 7 all-encompassing invariants that culminate with a mutually exclusive vertices signature, which is, in essence, the complete invariant. GIPSY is the first program that actually solves the graph isomorphism problem. Right now, it's working with covering designs and with Johnson's graph. GIPSY's approach is different than conventional wisdom school of thought in that it looks at everything from a number standpoint. It completely detaches itself from any conceptual ideologies of graphs and looks at graphs strictly from a numerical standpoint. What GIPSY is a solution in polynomial time for the graph isomorphism problem. PONG is a combinatorial optimization problem solution program. The acronym stands for Proactive Optimization Network Graphs. It is akin to other combinatorial optimization problem tools such as simulated annealing and the genetic algorithm, in the sense that they all try to find the optimal solution to a combinatorial optimization problem. How PONG differs is that it has a built-in formula that helps to actually help prove the lowest bound, that the optimal solution has actually been reached. Furthermore, another distinguishing feature of PONG, it also tries, and many times you can find all the non-isomorphic solutions at the global optimum, which helps to prove that the lowest bound has actually been reached. What's great about PONG is that you have many tools to prove the lowest bound, one of them being the formula, and the other one being finding all the non-isomorphic covering designs. So much work has been carried out for C1263. There have been a lot of articles that have been written for 1263. And so it's like a classical search that was carried out. Dan Gordon, he did 1263. There's one of the papers he did was 1263. And much work has been carried out on 1263. So in this case, we know beforehand the actual number of non-isomorphic covering designs, which happens to be 68 because it has been proven. There have been exhaustive searches carried out by Mr. Klas Markstrom, who is a professor from Sweden, and he did comprehensive searches using the supercomputer facilities at his university, and these searches took a long time to carry out. A lot of the demos, not all the demos though, have been ascertained by searches that Mr. Klas Markstrom carried out. The program that he used was written by Brendan McKay. It's called Naughty, and he carried out all the searches, and he was diligently carried them out, and with a lot of determination and patience. And his searches were very instrumental. In this particular demo, there is no starting point. It first finds the lowest bound, which happens to be 15, which is known, and then it proceeds to find all the 68 non-isomorphic covering designs. It usually finds the first 67 very quickly. The 68th one sometimes takes a little bit longer than other times, but because uses a random number generator, it is stochastic, and as such, it will yield different timing results with every run that you actually try. One thing for sure is that there's always room for improvement. There is no such a thing as fast enough. Some of these things can take a long time, and speed is never fast enough. You can always be faster, but there's also, apart from the physical speed, there's a methodology which PONG coupled with GIPSY allow searches to be done much quicker than would by just doing it using conventional speed from physical speed. This is all being run on a Intel Core i7-6700 CPU, 3.4 gigahertz, using 16 gigabytes of installed memory. At the beginning, PONG kicks in to find the lowest bound, which happens to be 15 blocks, but it does not start as a covering design. It's an actual empty kind of covering design, so it proceeds to quickly find the lowest bound. As you can see, as I mentioned before, the first 67 non-isomorphic covering design are found very quickly. Sometimes the 68th is found also quickly. Sometimes it takes longer than others. So here we're going backwards to show that as you can see here, all the non-isomorphic covering designs are found one at a time. And here are the actual set of blocks, the 15 set of blocks for each one. And as you can see, the times are shown here. If we stop it over here, the yellow shows what time it is now. The green is when it started. The red is how much time has elapsed, and this one is how much time has elapsed since the last non-isomorphic covering designs. And finally, and most importantly, this is the tally of the number of non-isomorphic covering designs found up to that point. As we were going backwards, so we're showing 3, 4, 5, 6, 7 as it would progress. But we know that we have to reach eventually 68, which is what we're looking for. Now, as I mentioned before, in this case scenario, we know that there are 68 non-isomorphic covering designs. But in reality, in real life, when we skip outside the boundaries of what we've done and what we've known, we do not know how many non-isomorphic covering designs there are, and that is one of the challenges, and that's what GIPSY and PONG working together are so good at, because they help to find most non-isomorphic covering designs, if not all, in order to help prove the actual lowest bound. There is always room for improvement. There is no such a thing as a program that is it's always an evolving science. There's always something to make it better and faster. But as it stands, it's pretty amazing compared to anything out there, GIPSY and PONG. But we will not just live on our laurels. We'll always strive to make it better and faster all the time. And there are ways that we know that could be used, which need some time to actually work them out, that can actually be implemented to make it even faster and more accurate in the future. But the ball has to start rolling somewhere, and we have to get, we're getting this out because it's so, it's so many uses, it's so ubiquitous that it will be able to really revolutionize how a lot of things will be done in the future, because of the power of GIPSY and PONG together, which have a synergistic effect on both the Graph Isomorphism Problem and combinatorial optimization problems. And that's the beauty of GIPSY and PONG together. working seamlessly. It will never be purely a science. It will be both, a composite of science and an art, and it will never be just science. There is some human decision making in these kind of problems. You want to maximize what is done as a science, but you will always have an interjection. You'll always need some human decision making because the numbers are outstanding and surreal, and there is no way beforehand to know what certain parameters will, how certain parameters will pan out. That is at the discretion of the user who will. It's a kind of feel thing, and there's also the science part, which can also be improved to make it more exact. That's always the case.